Thanks a lot, Avi, for accepting our invitation, and welcome to Moscow.
All right. Yeah. Thank you very much, Yanni. It's okay. Good. So everybody can see this, I assume, or tell me if not. Thanks for the invitation. I'm really happy to be in this forum and to see so many people from so many different countries and continents. I want to tell you about some work that I've been doing in the past 5 years. I mean, the title, main title is Geodesically Convex Optimization, which I'll explain. The subtitle, which was designed so to attract you to the structure, is can we prove P different than NP by using gradient descent? I'll explain this too. This work has been done with quite a number of collaborators that you see here. Some were students when we started, and many colleagues, and it's just growing bigger and bigger. So I'll tell you about this also in a second. I just want to use I use every lecture now to advertise my book. Because what I'll tell you about is evolution of research that is really based, grounded on computational complexity. Certainly my motivations are from there. It will touch many other areas, but and those of you interested in computational complexity and the interaction between mathematics and computer science, I wrote a book for you. No background is needed really to start it, and see lots of wonders that are, of course, I'm not going to talk about. You don't need to buy it, even though I really love the design, which I designed myself of the cover of the book. But otherwise, it's free on my website. So, and I really love comments of any type because I'll revise it at least online. Okay, good. So now we are done with that. Let me start with the lecture. So I'm going to tell you about this story. It's a long story, but I'll focus it around one problem and one algorithm and evolve from there. The problem, which I'll define, is the singularity of symbolic matrices. The algorithm is called alternative minimization. Will be explained. And there are several rounds to, the evolution of this story and to our understanding of it. And it's more or less a repeated process where we had something and then we internalized it and understood it better and then generalized it. And this includes the algorithms we had, the problems we looked at, the tools, and so on. And I'll reach, the state where we are at today, but I'm sure there's plenty more to do with it. The upshot is that one can extend the very familiar optimization tools used in standard Euclidean spaces to geodesic convex spaces, namely optimize on Riemannian manifolds in general, not just Euclidean space. And that one can do it obtaining concrete quantitative bounds on the convergence of these algorithms. But I also show you a lot of why to do it and how things came about. So one of the most amazing things to me in this story is how many areas of mathematics, computer science, physics it touches. Some are listed here. You don't have to read it all, and certainly not the subtitles, because I'll come to many of them again, but I'll just read you the green part as the non-commutative algebra, in fact, quite a bit also of commutative algebra and representation theory. There is invariant theory, quantum information theory, analysis, operator theory, statistics. And where I come from, computational complexity, like almost everything I do, it just comes out of failed attempts to prove lower bounds, hardness results. And it happens to touch on and develop new algorithms for various optimization problems. So some of these are tools, some of these are application areas, some of these are inspirational points and just magic connections that, again, we'll see some of. And yeah, I'm sort of stunned by the way that so many things converge around, as you'll see, a very simple, at least to define problem and algorithm that we start from. So I want to tell you about this. I don't know, by the way, what's the normal thing in the seminar. Just feel free to, I mean, we are a lot, but still, if you think something is, it's really not understood, just ask me. Or I don't know, or chat to the organizers or whatever. I'm open for questions. It's really nice that it's a more relaxed forum and has more time than the usual seminar. So I'll try to go slow and start easy. And the problem I want to, so again, I repeat this problem and the algorithm that I want to tell you about. And actually, I'll get to them, each of them, with a simpler example, and then we'll get to the real problem. Okay, so what is the problem or the problems? And here's the baby one. The baby one you should all be familiar with is the problem of finding a perfect matching in a bipartite graph. So you have this bipartite graph. You can think of it as as many parents who have kids who like or dislike different candies, and you want to give a candy to each child in a way that each child gets only a candy they like. In this particular graph G prime, there is a way to do it, but of course there are graphs where you cannot do it, like this one. And I give you a graph. You want to determine whether it does or does not have a perfect matching. A classic problem, combinatorially, algorithmically. We all know what to do with it. Everybody knows that it has a polynomial time algorithm. I'm not sure that you know that it was first discovered by Jacobi. I mean, more or less the same algorithm that is taught with the augmenting paths, where he was studying systems of ordinary differential equations. But anyway, there is a fast algorithm for it. P, I'll throw out, there will be complexity classes here. P is a class of all problems solvable in polynomial time. And one of the great insights in combinatorics is that sometimes it's good to phrase problems algebraically, and we get more insights into them. So even though this problem has a simple algorithm, here's the algebraic way to phrase it. One can look at the adjacency matrix of this graph, right? So you have a 1 or 0 in every entry according to whether there's an edge between the two respective vertices. Let's call this matrix A sub G. And now to say that a graph has a perfect matching is the same as saying that its permanent is positive. Well, of this matrix is positive, well, the permanent is just the hopefully familiar cousin of the determinant, where you just have the same formula, you sum over all diagonals, but without the signs. In determinant, you have the signs, in permanent, you don't. So there's an algebraic way to capture this problem. Of course, many of you know that permanent is sort of an unfriendly polynomial. It's very hard to compute. And of course, we are only asking whether it's positive or not. So this problem is not hard. We know that already. But still, permanent is a complex polynomial. And it turns out that there is another, what leads us to our problem is another algebraic formulation of bipartite matching due to Jack Edmonds about 50 years ago, which is the following. He suggested putting another matrix to represent the graph. Here, the matrix is the matrix of variables. In every entry, if it's a 0, you leave it at 0. If it's a 1, you put there a variable that's special to that entry. So in position 1, 2, We had a 1, now we write a variable x12, and so on. So that's a matrix of the, another matrix, symbolic matrix. So you see already symbolic matrices. Symbolic matrix, which captures this graph. And now it's a very simple observation that G has a perfect matching if and only if the determinant of this symbolic matrix, which is now a polynomial, of course, is not identically 0. Okay, why? Because because the variables are distinct, so there will never be any cancellation, even though you have minus signs in the determinant. So that's a very simple observation. The problem of testing this determinant, you never want to expand it. The determinant is, symbolic determinant, it has exponentially many terms. But just to test non-zeroness, it's still the perfect matching problem. It's in P. And what was Edmond's great insight is to ask the following question. So suppose instead of variables in the entries of the matrix, you allow arbitrary linear forms. Okay, so that's his big question, and which is still open. And in fact, one motivation for giving these talks is just asking you to work on it. So what's the problem? The input is a symbolic matrix, so every entry has a linear form in some number of variables, x1, x2, and so on. You can think of the field as the rationals for this talk, even though it's interesting over any field, but let's stay with the rationals here. And one way to give it as an input, of course, a linear, matrix of linear forms like this is easily described by a linear combination of matrices, right? So you just give the coefficient, the matrix coefficient of x1, matrix coefficient of x2. So you really get a bunch of matrices, A1, A2, and so on over your field, and they define this symbolic matrix for you. So this is the input. And what do you want to know? You want to know whether when you evaluate the determinant, which is a polynomial in these variables, you get identically 0. This is what I call SING, or the singularity problem. Okay, so I hope this is clear. It will be good to understand it. So it's some kind of generalization of the perfect matching question. This is what we want to solve. Now, Edmonds asks whether it's in P. You can, at this point, if you've never seen this, you might wonder, well, it's a natural problem, that's for sure, but it turns out to be far more important than it looks, and this took time to discover. First, regarding its complexity, Lovaas, the mid-70s, were the years where randomized algorithms blew up and became a real field. And he observed that this particular problem has a very fast probabilistic algorithm. RP is randomized polynomial time. What's the algorithm? You just plug random small integers into these variables, x1, x2, and so on, and then you evaluate the numeric determinant. This, of course, is very easy to do. By Gaussian elimination, say, and as a polynomial time algorithm. So the point is the following, that on the one hand, if the determinant is identically 0, the symbolic determinant is identically 0, then of course, no matter what you plug in, you'll get 0. On the other hand, if the symbolic determinant is non-zero, then the probability you land in the variety is very small. So that's why it's a good probabilistic algorithm. So this problem is a fast probabilistic algorithm, but we are interested in a deterministic algorithm. That was Edmond's question. So, I mean, many, practical people would say a probabilistic algorithm is good enough. So why worry about a deterministic algorithm? Well, my view is that you should always try to get deterministic algorithm. I invested many years in studying this question, but this particular problem is particularly important. So let me explain why. One is the discovery of Valiant, it's the same year, but a different universe, that this problem, symbolic determinant, captures all algebraic identities, and by all I mean all. Every identity, algebraic identity you find in any textbook of mathematics, can be described, reduced to this problem. This is a complete problem in our language, complete for the class VP of Valiant polynomial time for arithmetic power computation. So it captures all our algebraic identities. We'd like to know if we can test these identities deterministically. But there are many special cases of this which are particularly interesting in various areas of mathematics. It captures the module isomorphism problem, it captures the graph rigidity problem, and many others. But really the sort of the shocking reason why it's important, and if you've never seen this and you're in for a treat, is this result of Cabanes and Impagliazzo from about 20 years ago. It says the following, so I'll do it slowly so you are duly impressed and really digest this well. If there is a deterministic algorithm for this problem, for this particular problem, singularity, then something like P is different than NP is proved. You have proved the biggest result in computer science. I put it in quotes because it's not exactly P different than NP, it's something similar. It has to do with arithmetic P and arithmetic NP. And I'm not going to go into this. It will be a huge result. But I want to stress something about this implication because it's so strange. I mean, the assumption is that some problem is easy, and the conclusion is that some problem is hard, right? Like NP-complete problems are hard. Or the permanent, in fact, will show that the permanent is hard for polynomial. So this result is not so difficult to compute once you know enough complexity theory, but it's amazing. And this is a major motivation to find this polynomial time algorithm. And this also explains the subtitle in my talk. I mean, well, it's partly explained. It at least says that P different than NP or lower bounds in general can be proven by finding algorithms. Hardness can be proven by easiness. So that motivates finding a deterministic algorithm here. So that's what we want to do. I said already we don't know how to do it, so we'll see what we do about it. Just for myself, this is a problem of de-randomization and a problem about proving lower bounds, and that's my main interest in this, and that's how I got into this, studying the things I'm going to tell you about. Okay, good. So questions so far? Everything's clear? All right. So I want to tell you, I mean, we can do something, but not this one. So I want to tell you about the dual life of symbolic matrices. So again, here is a setup. I'll give you a symbolic matrix. And I want to know whether this matrix is singular, right? Whether the determinant is identically zero. And that's another way to ask it is whether this matrix is a singular matrix, singular where? Well, obviously, if the variables commute as you all assumed, and I didn't expect otherwise, then it's a question of whether it's invertible or singular in the field of rational functions over these variables. And as we said, we know the status of it. So far, all we know is that it has a probabilistic algorithm, but we don't know whether it has a deterministic one. But like all mathematicians, when we can't solve a problem, we change it, and we'll change it here, and we'll study the case where the variables do not commute. And it turns out to be also a very important and well-studied problem. The first is, what does it mean singular for a symbolic matrix in non-commutative variables? Well, there is an appropriate field, it's called the free skew field, where you want to invert it at, but there are elements, this is a highly non-trivial object to define, and I will not do it here, but you will see equivalent formulations of this problem, which are elementary. So we are asking whether this matrix is invertible in non-commutative variables. So what's the status of this problem? Well, it looks pretty hard. I mean, it took quite a bit of effort to even find a decision procedure for it, as opposed to the commuting case where it's obviously decided in exponential time, right? So Kohn developed a theory and proved that it is decidable. And the best upper bound before we started working on it was the exponential time. There was no probabilistic upper bound known that's more efficient. That was the status of it, just by Kohn and Rethenauer. And the first half of the talk will focus on this result from about 5 years ago, proving a deterministic polynomial time algorithm for this. Okay, this is with Gard, Gurwitz, and Oliveira. And yeah, so I'll say quite a bit more about this. I just want to point out that shortly after we did it, a very different algorithm was discovered that handles practically all fields by Ivanios Subramanian. That is, as I said, very different. So ours is analytic, theirs is algebraic, and the whole talk will revolve around this analytic type of algorithm. It's also strange and curious that an algebraically formulated problem has an analytic algorithm, and I'll explain what analytic means soon. Okay, so we'll focus on this. So that's what we want to solve, and I now want to start describing the algorithm, and to do that, I'll first describe an algorithm for the matching problem, because it will be an extension of that algorithm. Okay, so we are going to describe an algorithm, and there's this alternate minimization algorithm, and let's see what it is. So I'm reminding you the bipartite matching problem, and it has this combinatorial description. It has the two algebraic descriptions that I showed you, but it also has somewhat of an analytic description that many of you may be familiar with, and this is a problem of matrix scaling. It goes back, at least 60 or 70 years to Sinkhorn, and even before. Sinkhorn was one of the first to define this algorithm for it. So I want to tell you what matrix scaling is. Imagine a non-negative matrix A. First, I need to define what a doubly stochastic matrix is. So doubly stochastic is a matrix that all row sums are 1 and all column sums are 1. Okay. And if the matrix is not doubly stochastic, we may want to make it doubly stochastic. So make it how? We are allowed to make it to do the following operations. We can scale rows and columns by scalars. So you can multiply a row by a constant or a column by a constant, or in pictorial terms or matrix terms, we are allowed to pre and post multiply the matrix by diagonal matrices. And what are we trying to do? We are trying to scale it, namely to make it doubly stochastic. So doubly stochastic scaling problem is to find out, given A, whether we can scale it so that it becomes doubly stochastic. And notice that I put approximately here. We don't really care about making the row sums and column sums 1. We really care much more about making them approximately 1. Approximate means that we can get them as close to 1 as possible as we want by better and better scaling factors. Why do I prefer this problem? Because this problem is equivalent to the perfect matching problem. Okay, so the question whether you can approximately scale a non-negative matrix is the same as testing whether its permanent is positive. So that's a different description of the matching problem. Why did people study it? Well, there are many reasons, and I won't go into that, but sort of started from numerical analysis point of view, signal processing, and then people used it to do combinatorial stuff. Actually, I'll show you this approximate permanent connection. And of course, as I said, it's equivalent to perfect matching problem. So how do you solve this?
Small question.
Yes.
Is it equivalent to the problem about permanent for non-negative matrix or for any matrix?
No, for non-negative. Everything for now is non-negative. It's very important.
I see. So it's really equivalent to the perfect matching problem, right?
Yes. So perfect matching, usually the entries are 0, 1, but you can think about the computing the permanent.
It doesn't matter for permanent,
yeah.
right?
Testing positivity of permanent for non-negative matrices. Very important. Thank you. Okay. Okay, good. So how do you solve this problem? I mean, I give you a matrix. How do you know if it can be scaled or not? Here's the ingenious idea of Sinkhorn, and actually earlier, it came up independently several times. We are going to just try it on one of the matrices I showed you. First of all, I want to point out that the problem is sort of fair. You have 2n conditions, maybe 2n minus 1, the roll sums and color sums, and you have 2n scalars to play with, right? So, but of course it's not obvious. And there are conflicting desires from the columns and the rows. But at least, I mean, this basic naive idea or greedy idea says the following: half the problem is easy to solve. If you want to make all the row sums 1, you know what to do, right? So you say, let's do it, and then worry about the columns. So that's the idea of alternate minimization. So we want to find these left and right, rows and column scalars. Seems hard to do it simultaneously, so we do it one at a time. So let's scale the rows first. Scaling the rows, this is a stochastic matrix, row stochastic matrix, right? Everybody's with me. This is going to be, sort of important. That's the first step of the algorithm. But of course, now the columns are not scaled. So let's scale them. We scale them, and now, of course, the rows are not, so you do the rows. And you continue doing it. You just continue doing it. And what happens in this example is that this is what happens. I mean, you'll eventually alternate between these two possibilities. So it doesn't look good, but there's no convergence of this algorithm. And maybe it's not so bad because this graph that we started with has no perfect matching. So it cannot be scaled. And so far so good. I hope the algorithm is clear. And maybe I should write it down, what the algorithm does. A very simple algorithm. I mean, just, you just iterate, scale rows and scale columns. Well, these diagonal matrices on the two sides are just the inverses of the row sums. And of course, you never get a 0 if you get a 0. I mean, if in a non-negative matrix, if a row sum is 0, they are all zeros, and then you can never scale it. Okay, good. So this is the whole algorithm. You repeat it here. It says n cubed times. We'll see why it's enough soon. And that's the alternate minimization heuristic. In general, alternate, we'll see more generally later, but you basically solve, maybe the problem is hard, but parts of it are easy. So you solve the easy parts again and again and again, hopefully to converge to what you want. Let's try it on this example. This is the other graph that we had in the beginning, which does have a perfect matching. And let's see what happens here. So when we scale the rows, we get this matrix, right? It's row stochastic. Then the columns are not good, so we can do this. Scale the columns, but now the rows should be fixed, so we fix the rows. And maybe you already notice, if you have a good eye, that things off diagonal are shrinking and things on diagonal are increasing. And in fact, it will converge to this matrix. So again, that's good because this was a matrix with a perfect matching. And of course, the bottom line is that this is a general phenomenon. Okay, so if we write the algorithm fully, we just iterate it n cubed times. And then we test whether, well, let's say we, the last step made all the row sums 1, we test if the column sums are very close to 1, let's say up to 1 over n in whatever norm you want. And, answer, if yes, then we say the permanent is positive, otherwise we say it's not, permanent is 0. That's the whole algorithm. And there are many different analyses given over the years to this algorithm, but I want to tell you about one that Lina Samornitsky and I did about 20 years ago, because, lucky enough, this was generalizable. This type of analysis was generalizable to lots of other algorithms of the same nature that I'll show you soon. Okay, what's the analysis like? So first notice, this is, I call this analytic algorithm. It's sort of a dynamical system, right? I mean, you just evolve a set of matrices by these operations, and so it's a process generating a sequence of matrices. And you want to say that they converge in some cases or don't converge. Let's say, I mean, it's very easy to see that if the permanent is 0, it doesn't converge. That's very easy. So if permanent is positive, you want to show that it converges, and in fact converges quickly. Almost, I think, all cases I know of analyzing this type of dynamical processes, you want some Lyapunov functions, some function that will be a progress measure, that say where you are making progress with your algorithm. And the progress measure we picked in this paper was the permanent itself. We picked, so this is sequence AI of matrices, and we pick the permanent as a progress measure. And once you do that, the analysis is extremely simple, really, really simple. So here it is. There are always 3 parts. First, you want to say your progress measure has some upper bound. And in this case, it's very easy to see if either row sums or column sums are 1, the permanent is at most 1, because the permanent is at most the product of row sums. So that's easy. All of them are upper bounded. Second, that there is progress at every step, that, from one step to the next, you grow by a non-negligible factor. In fact, this star near growth says that you grow as long as you have room to grow. So as long as you didn't satisfy being close to a doubly stochastic, you'll grow by something like 1 + 1 over n.
What is n?
Sorry?
What is n?
N is the size of the matrix. It's an n by n matrix. Thanks, maybe I didn't say this. It's an n by n matrix. Okay? And for now, I'm using, it's actually a very good question, because I'm demonstrating the analysis for 0, 1 matrices. If I were to do it for rational matrices, then n would be simply the total size of the, the bit length of these rational entries. So it's really the input size. N is the input size. But for 0, 1 matrices, it's just the size of the matrix. Did I answer your question?
Yes, but how could it stay below 1 if it grows by 1 + 1 over n?
Yeah, so you see the green star near growth. I said that as long as there is room to grow, so as long as the test performed by the algorithm here, if this fails, then there is room to grow, and you will grow. Okay? And if you pass the test, then you stop, so no problem. Okay?
Thanks a lot. Now it's clear.
No, that was very, very good. Thanks.
Avi, can I ask you also something?
Yeah.
So you start with a 0, 1 matrix, but in the process, it gets more and more complicated. So this 1 over n, when you say, when you mentioned now this input length, would it actually turn into this?
No, in this case, it will be 1 over n. It will remain 1 over n. And another good point you raise is you want to make sure that these rational numbers don't become too long, and you sometimes need to truncate them, and you need to argue this as well. But I'm not going to go into these details. But it's the same n here. N will be the original input size. Now this is, the proof of this is really simple. I could do it, but I won't, but it's just a simple application of arithmetic mean, geometric mean inequality. So what's the third part of any analysis of this type? You want to say that you start not too small, right? And in this case, in the Boolean setting, it's very easy to see that in the beginning, after one step of the process, let's say you normalize the rows, the permanent is at least 1 over something like 1 over n to the n, right? It's not smaller than exponentially small. And because of this, you grow by 1 plus 1 over n. It's very easy to see that the total convergence time to being very close to doubly stochastic is polynomial, let's say n cubed steps. So the whole thing is, half a page of a proof. So it's a very simple algorithm. And I also want to stress that this is an algorithm for perfect matching, right? I mean, that's what it did. It just computed whether permanent is positive or not. It's much simpler than the algorithm we are taught in school, in college, in algorithms classes, how to solve the perfect matching problem. So I think this one should be taught as well. It's very different, and I find it very elegant. And the other thing here stressed in this green thing, this step of lower bounding the permanent in the beginning, this progress measure, was extremely easy in this case, but that's exactly the thing that will get harder as we move on. So let's move on to the next step, to the real problem of operator scaling.
I'm sorry, may I ask one more question about this algorithm?
Yeah.
So will this algorithm catch all perfect matchings? Meaning, if a cell is contained in some perfect matching, will it be positive in the limit?
That's a very, very good question. You ask great questions, everybody. So the question is in the picture here. Oops. In the picture here, you see the diagonals are 1s and the others are 0 in the limiting process. And in that particular graph, this was the only perfect matching. The question is whether you'll get positive for edges in matchings and otherwise not. And the answer is actually simple. You'll get a positive number if the edge participates in some perfect matching, and you'll get a 0 if that edge does not participate in any perfect matching. So it will.
So if an edge participates in any perfect matching, it will get a positive number.
That's right. That's right. If and only.
Very good.
But thanks. Actually, the next question to ask is, what do these numbers mean? And the answer, I don't know. It certainly does not capture the fraction of perfect matchings it participates in, because if it did, then we'll have a deterministic approximate counting, right? Anyway, yeah, but yeah, it's yeah.
So should it count weighted perfect matchings somehow?
No, I don't know. It's an open question, and I wish somebody looked at it. I mean, I looked at it some, but I don't know the answer to this. It's a fascinating question. Yeah.
Thanks.
Okay, good. So let's continue. Okay, so we are done with the baby version, and so this was all known. Now I want to move to the operator scaling and to the non-commutative singularity problem, and talk about two papers. A Guritz paper that just followed this paper I had with Linar and Samolnitsky, really, performing a quantum leap. And then its analysis, which we did in that, together with him and Garg and Oliveira about 5 years ago. So what is a quantum leap that Guritz did? He extended sort of quantum generalization of what might be called classical matrix scaling problem. And it's called the operator scaling. So it's some quantum generalization of the perfect matching problem. How do you do? So let me do a cartoon version of quantum generalizations in general. I hope there are not too many quantum physicists in the audience who will be offended by this, but basically, you go up in dimension, right? You have a matrix, you move to an operator or a tensor, many matrices. You move from L1 to L2, defining what scaling or doubly stochastic means is a very natural thing. In the case of matrices, we just pre and post multiply by a constant vector. Here we take, this some AI transpose and want it to be the identity. If you think about it and you think that all your matrices were diagonal, then you'll get exactly back to the matrix scaling problem. So it's really a natural generalization of what being scaled or being doubly stochastic means. And the allowed operations, beforehand we multiplied by diagonal matrices, which are vectors. Vectors generalized to matrices in quantum, when you do quantum analogs. And so now we are allowed to pre and post multiply each of the matrices in this tuple, A1 through AM, by some invertible matrix on the left and on the right, but the same one. So that's the analog, and I want to say why go with sort of this analog. I mean, you already see a tuple of matrices, which should remind you that we were interested in the symbolic determinant problem, in the Edmonds problem. So that's exactly why he thought of this generalization. Here's the problem we initially were interested in, right? You're getting a tuple of matrices, which represent a symbolic matrix. And we want to know whether it's singular in the commutative case, which is what Gurwitz was after, or in the non-commutative case, which we will solve. And he said the following, and that's part of the beauty of this evolution. Tuple of matrices can mean lots of things in lots of areas. So it can mean just a symbolic matrix, but it can also mean a tensor, or in fact a positive operator in quantum information theory. So what is a positive operator? It's a generalization of a non-negative operator. It's a generalization of non-negative matrix. Is the following. Here's a linear operator on matrices P. You just take the matrix P and apply to it some AI P, AI transpose. Okay, think of the AI as complex matrices. Okay, that's the most general quantum operation on a quantum state. It takes PSD matrices to PSD matrices, and that's important in quantum information theory because usually these matrices represent their density operators, so the general description of a quantum state. Anyway, it's a simple linear transformation given by this tuple of matrices. And, as we mentioned before, and Gurwitz noted, there's a notion of scalability, making it doubly stochastic, such an operator. It's really applying it to the identity. You get back to the identity, both the operator and its dual, where you reverse the transpose with its rows and columns. So he said, maybe we can scale, an operator, and maybe it's related to this singularity problem. And in fact, he proved this one direction. So he asked whether one can scale or not an operator, and that's why it's called operator scaling. And he proved this one direction. If you cannot scale an operator, then again, scale by pre and post multiplying by non-singular matrices, by invertible matrices, then the symbolic matrix this tuple defines is singular for commuting variables. He couldn't prove if and only if, and the reason he couldn't is because it's not true. And one of the important steps to start understanding it better was realizing that it's actually the if and only if holds if you care about non-singular or non-commutatively singular symbolic matrices. So really scaling it is the same as scaling matrices for the perfect matching problem. It's a really analog. Non-commutative singularity is the algebraic analog of the perfect matching problem. And there's a scaling approach here. And further, Gurwitz designed an algorithm that looked just like the algorithm we had before, an alternate minimization algorithm, which just tries to, left and right, alternating scaling rows and columns in this sense of operators. So here it is. You don't have to read it. I mean, you can just believe me that it's exactly the same algorithm. I made it sure it looks the same. There's an obvious way if you want to make it row stochastic, namely satisfy, let's say, this equation, or you want to make column stochastic, satisfy this equation. There's an obvious matrix to pre or post multiply by so that it will happen. So you can always satisfy half of the constraints, and then you just iterate them again and again and again. And at some point, hopefully in polynomial time, what you want to do is stop or check yourself whether it's already close enough to being doubly stochastic, and then you stop. And then you guess that, it really answers your original question about whether it's invertible or not in non-commuting variables. So that's, he thought about commuting ones, but anyway, I'm telling you already what we know. And that's the algorithm. And he made the following observation. Well, first of all, if we want to analyze it, we need a progress measure. Again, this will generate a sequence of operators. We want to show we are making progress. The progress measure it shows is called capacity. Again, you don't have to read it. That's the analog of the permanent in the previous case. It's roughly the worst ratio you can get between the output and input of this operator on positive definite matrices, or the determinants. No reason to remember it. There's a natural progress measure, but once you pick it, the analysis is exactly, well, first of all, this measure captures the answer just like before. It will be singular if and only if the capacity is 0. So it will be non-singular if it's positive. So just the same picture with in the baby case. And the analysis, I said we do the same. It's very easy to argue that all capacities in this process are bounded by 1. It's really easy to show that as long as you have room to grow, you will grow by at least 1 plus 1 over n by the same AMGM argument. I mean, it's all identical, really. And what he got stuck at is proving that there is some exponential lower bound on the capacity in the beginning as long as it's positive. So it turns out that this is actually hard and certainly non-elementary to the best of my knowledge. And that's really what we did in this joint paper that solves this problem. So that's the thing we provide, and I want to tell you something about where it's coming from. Okay, but I just want to say 2 things. Of course, it immediately, once you have such an exponential lower bound as before, it gives a polynomial upper bound on the number of iterations. And the source of this bound is actually invariant theory. So there's some group action hiding there that I'll exposit, I'll sort of make clear. The measure is sort of an invariant of this action, actually a semi-invariant. And the analysis comes from understanding degrees of invariant polynomials. I'm going to tell you about all of these in a second. Okay, so but basically, in order to prove the lower bounds here, you need and analyze this process. You need some tools from algebra. So I'll tell you about this, but beforehand, I want to tell you about what this algorithm actually solves. So I mentioned to you that the tuple of matrices can come up in lots of settings, and it does. And here are 6 different settings where a tuple of matrices describes some problem. In linear algebra, in algebraic complexity theory, in quantum information theory, in non-commutative algebra, in invariant theory, and in analysis. And in all these cases, you get a natural question about this tuple. These questions seem to have absolutely nothing to do with each other, seriously. I mean, some of these connections are very subtle. Most of them were known, but in different areas, so it was great to discover all these connections. Some we had to prove. But once you solve one of them, and we did solve one of them, you solve them all. So because they are really all equivalent. So it's sort of amazing that all these problems in these different areas are equivalent. Well, the last one is a bit, weaker than all the others. Certainly, solving the others implies solving it. And I mean identical here, not in the sense of reductions in empty completeness. Identical, namely the answer is yes for one for a given tuple, if and only if it's yes for any of the others. Okay, so there are really identical problems popping up in different fields. In fact, some of them are not just natural, they are crucial. Like in non-commutative algebra, this question of testing singularity is really the word problem for non-commutative algebra, whether an expression in non-commutative variables is identically zero, or whether two of them are identical. So basic and important questions are represented by this, and because of this algorithm, all of them have a polynomial time solution. So it's really nice that so many different problems in different areas are identical and are solved by the same algorithm. Okay, so now, so that's I'll ask for. So I've been talking 45 minutes. Okay, good. Let me ask for questions. So now I want to move to invariance.
Organization question. Do you want to have a break of 5 minutes, or do you want to continue?
I'm happy to continue, but if anybody, I'm happy to continue. Okay. It's not 2 hours, it's just like 75 minutes. Yeah, let me continue if it's okay. Yeah. Okay, so I want to tell you about,
one small thing. I'll just send the link to everybody, and that's the link where the seminar will appear later, because I forgot to mention it in the beginning, for those who don't know.
Okay.
It's just a YouTube link.
So I'll give you sort of a one-slide crash course on invariance theory in the next slide, but just for people who've never seen it or didn't see much of it. It's something I had to learn, right? I mean, I didn't know anything about it 5 years ago. So the invariance theory is all about symmetries, which are the real hero of the story. Symmetries in mathematical language are group actions, and we'll talk about their orbits and invariance. So let me give you a couple of examples that I'm sure you're familiar with. Here are 2 graphs. They are isomorphic, right? There's a group acting on the vertices that transform one to the other. And that's one example of a group action. Another example is, the group which is time acting on these states of a billiard table, right? We kick the white ball and then it evolves, the state evolves. You get an evolution here as well. And here's another example. You can take any shape and then cut it with scissors and create another shape from it. Let's say you cut in straight lines and you don't overlap the pieces. So there are lots of, I'm not sure I can describe the group here, but it exists in some sense. And, in all these cases, you get, there's a dynamic thing happens. So you start with one object and there is an orbit of everything else you can evolve to by applying group elements to what you're given. So that's an orbit. And despite the fact that there is, it looks dynamic and there are many different things you can reach, what invariance theory studies is what doesn't change in this kind of process. And again, you probably have seen, examples of this, like these are the invariants of the action. And in this particular case, the famous result that the only invariant in this kind of transformation is the area. Area is, of course, preserved, but nothing else does. That's the only invariant. In physics, you learn that energy and momentum are the only invariants preserved in this elastic collision model. So there are functions of the state that don't change. And in the graph isomorphism, I don't think we have an understanding of the invariance. So, yeah. But anyway, that's a setup. And for us, from now on, we are going to look at not at these examples, but examples where the acting group is a linear group, say a group of matrices. I'm suppressing technical things like you need to look at reductive groups only, and the action on vector spaces is has to be algebraic action. But don't worry about this. Just think of matrices acting on vectors. And somehow, luckily, this theory is very well developed, and we have algebraic part, which in particular says that all invariants are polynomial invariants in this case. And we have a geometric part, which understands the space of orbits and gives us a non-commutative duality, which we'll meet soon. Okay, here's the one slide crash course. I just want to tell you, you are familiar with these things from even from college. So think of a group of matrices acting on a vector space. For now, assume that we are over the complex numbers for niceties. First of all, the orbit is everything you can get to. So if you have a point V, a vector V, all the G times V, this is the orbit. And actually, because we are in C or R or whatever, closed, looking at closures is very important. All the limit points of orbits, that's really even more important. So we have orbits and orbit closures. The other thing is we have invariants, invariant polynomials. This is the set of all polynomials acting on these variables. If we have k coordinates, then we can think of having k variables. All the polynomials that do not change invariant, right? When you apply any group element to the vector of variables. Okay, so these are the invariant polynomials. They are the subring of all polynomials. This is very important to understand. And a couple of examples. If the group is a symmetric group acting on vector by permuting coordinates, then you know the invariant ring, I'm sure. This ring of all symmetric polynomials, and particularly generated by very few polynomials, right? As a ring, it's generated by elementary symmetric polynomials. Another example you are familiar with is here the vector space is the vector space of all matrices. So it's really n-squared variables. And you act on it by changing bases from the left and from the right by non-singular determinant one transformations. Okay, that's a group action. And if it's sort of Zoom talks are really a pain. I cannot look at you and ask you what do you think it is and so on. But anyway, also here, it's very simple to see that there is only one polynomial invariant, just a determinant of the given matrix. It doesn't change, and that generates all invariants. And in these two examples, you see that the rings, which are infinite, are actually generated as rings, as algebras by a finite number of generators. This is a fundamental result of Hilbert. This is true for any invariant ring of such an action. That's absolutely crucial for us. People probably know that these two papers he wrote in 1890 and 1893 started basically modern commutative algebra. This is where the basis theorem is proven, and Null-Salensatz is proven. All these things were proven as means to get this result in invariant theory, but of course they later did lots of other things. Once you have finite generation, one thing you should be interested, it's very natural, is these polynomials that are generators. How small can their degree be? And this turns out to be absolutely crucial to the analysis. So when I said non-trivial tools are used for this analysis, for this lower bound, on capacity, for example, this is what's used, degrees of generators of invariant rings. The last concept in this, which we'll see a lot from now on, is the null cone of a group action. What is a null cone? It's all the points that look like zero. What do I mean? When you apply a non-trivial invariant polynomial, you get a zero. That's what you will get if you plug zero. Zero is the vector of zeros, right? The origin. That's called the null cone. And it's absolutely crucial that this null cone, which is an algebraic variety, more or less by definition, is actually has an analytic description. And that will come up basic result by Hilbert and Mumford, you are in the null cone in this variety if and only if 0 is in the orbit closure of your initial point. So in other words, you can drive the norm of your input vector by group elements as close to 0 as you want. Okay, this connection will come up. You also don't have to remember this, but just want to point out that the null cone is a very important concept for us, and you'll see it soon. Okay, questions about this? You don't, as I said, this is some background material to just say, don't worry about if you've never seen it before. What you need, what I'll need from you is, I'll explain again. But anyway, questions about this? Okay. Yeah, so
excuse me, may I ask you?
Yeah.
It seems that your first, fourth, and fifth, and probably second directions can include two algebraic geometry, commutative and non-commutative linear algebra. This is the linear algebraic manifolds. Invariant theory also includes in algebraic geometry. This is my statement and also question.
Yes, I'm not sure what is the question, but it's absolutely true that this is questions of representation theory in algebraic geometry come up when we need to analyze further algorithms that I will show you. So for the first one, for the one of operator scaling, just degree bounds on generators of this particular group action are sufficient, but for more complex actions, we'll need more, and I'll talk about it. Yes.
Thank you. Thank you.
I just wanted to show you what are the null cones in these two examples. In the first one, it's a finite group, so there are no limits here, and the null cone is the only point which looks like 0 is a 0 point. And a vector of all zeros, you permute it, you get zeros, and that's the only one with this property. But in the case of this basis change example, the null cone, you'll probably guess, these are all singular matrices. So it's very natural objects, these null cones, and we'll see, we will meet more natural objects like this. So this null cone membership, whether a point is in the null cone of a group action, turns out to be fundamental, and in fact, we'll see that it's sort of dual to the scaling problems we looked at. And another point is that null cone questions capture lots of problems that you know about, and we'll see examples, where mostly these problems, when you hear them stated, don't mention at all groups or symmetries. So sometimes you have to search for the symmetries, and this is really good and important for algorithms. Okay, so we'll see that too. So we are going to do 2 rounds of unification and generalization of the algorithms we saw so far. So here are the two problems we looked at and algorithms for them. We for both use alternate minimization. In both cases, and now it's important to stress, we said diagonal matrices, or we said invertible matrices, but now I want to stress that these are groups. And these are really group actions on the left-hand side on matrices, on the right-hand side on tuples of matrices. So we have a group action, and this is going to be used in the analysis. And the goal of the problems were scaling, and we'll talk about this, as I said, connection between scaling and null cone problems. But the upshot is here, it's really important from now on to remember that the algorithms we described are actually taking place in an orbit of the input. You're just applying these group operations to the left, to the right, doesn't matter, but you are remaining in the orbit. That's very important. Okay, what are the general problems we can solve with this just the same heuristic? It's alternate minimization in groups. So first, just a word about alternate minimization. I mentioned it already, this heuristic where you have a complex problem to solve, a function of many variables, doesn't have to be two. You know that if you fix all but one of these, then the problem is easy, like scaling the rows or scaling the columns. So it doesn't have to be an optimization problem. It can be a sampling problem, like maybe many of you know global dynamics. This is also alternate minimization. You know, this Monte Carlo Markov chain games. You've seen lots of examples of this in statistics, optimization, machine learning. Many times we don't understand convergence at all. Sometimes we know convergence and have no bounds for it, and so on. This is very important to understand heuristic, and we understand it for groups. So what do I mean by alternate minimization of groups? I'm just generalizing what we've seen before. Imagine that you are acting, your vector space is a K tensor. It's all K tensors in some dimension K. And the action is you have some product of groups, like before we had two, but in general you would have K. They can be either diagonal or linear groups, and even more, but let's say products of groups. They each act on a fiber of this tensor in parallel, right? In all fibers in a particular direction. And there's a natural notion of scaling. You are trying basically to make all marginals of this tensor uniform. I'm not formally defining it, but that's, you know, it's very natural, like we did before. And so the problem is, this general scaling problem in this setting is I give you a tensor and I ask you to scale it. Is it scalable? And the main result here is that we can do it for any one of these problems, and indeed efficiently, right? So alternate minimization, this simply heuristic, will scale any input vector so that the result, or whatever, this point in the orbit V prime and the orbit of V will be epsilon close to the scaled target, and we can do it in polynomial time in all parameters. I want to stress that this is a non-convex problem, right? It's in fact, even the domain is not convex, it's just a product of groups, right? So it's a non-convex problem, nevertheless, has an efficient algorithm. I want to mention a few applications of this beyond the two I mentioned. So we want to test whether input vector or tensor is scaled, or otherwise the dual will turn out to be whether it's in the null cone of the group action. We saw matrix scaling and operator scaling as examples. If you move to 3 dimensions, it turns out to get something called the asymptotic Chronicle coefficient problem from representation theory. For general K, you get the entanglement distillation problem, a basic problem in information theory about quantum states that have held by K parties, and you want to basically maximize the entanglement between each player and all the others. And it's related to the slice length problem, which got very popular recently in combinatorics, and there are many others. So these problems really exist in abundance, and we have this algorithm for them. And moreover, you can guess this by what I said before. The analysis of this is exactly the same. I wanted to stress that while this is polynomial in the all parameters, sometimes convergence in 1 over epsilon is not enough, and we'll actually say something about this. Anyway, the analysis is exactly the same, and it turns out that there is a universal progress measure to choose. It's just the L2 norm. You basically run the same experiment as before, and you see that you can bound each element in this evolution in the orbit by some bound, like 1, that this norm grows or shrinks. It depends what you want to do, but let's say grows by 1 plus 1 over n, and you want to prove that you start not too small if you are not in the null cone, if you're not just going to get 0. And this just requires more tools from invariant theory and representation theory that I will not be able to explain.
May I ask some question about complexity of the problem?
Yeah.
1 over epsilon, is it a number of iterations to solve?
So the number of operations will be polynomial in the description. It's a rational input, let's say. The number of bits in the input in n is the number of coordinates, and 1 over epsilon, which tells you how close you want to get to the target. So what was your question?
And also, is it upper bound?
Yes, it's an upper bound. Yeah. So it's an upper
can
bound.
it be even simplified? I mean, can we solve it faster?
Yes, and I'll show you exactly in which context. Yes, very good question, but we'll get to it. Okay.
Thanks.
Yeah, sure. Okay. Here's the, you see this result or even the previous result, and something should start bothering you, right? I mean, this is a non-convex problem, and somehow a simple greedy procedure converges always and even quickly. What's going on? Another question, what connects is scaling and null problems, which I mentioned are dual. Why are they? Why did I say this? And what do you do if you are not in the alternate minimization case and you don't have this, you don't have parts, you have just an arbitrary linear group action. What do you do? I will answer all these questions. So we'll see soon what to do. And this calls for the second generalization of this game. We'll see non-commutative duality, and we'll see geodesic convexity and the moment map. So let me explain these things. So here again are the examples we've seen, and where there was a goal and there was an analysis for it. The goal was to scale, and the analysis had some minimization of some potential function, permanent capacity or the L2 norm of the vectors. And what I want to do now is to switch the analysis with the goal. We'll start from trying to minimize the potential function and see what we get. Right? We'll start from different problems. It's sort of really curious because both of them are natural. Scaling problems arose naturally in all the contexts I mentioned, and also these minimization problems are very natural. So let's try with the end, start with the end. So we have an arbitrary group now, not necessarily a product, acts on some vector space, okay, G acts on V. And what we want to do is, given a vector, we want to ask what's the minimum norm object in the orbit, as you see in the picture, okay? What's the lightest vector in the orbit of V, in the L2 norm? It's an optimization problem, and as I mentioned, it's a non-convex optimization problem. In particular, we can ask whether this minimum is 0, because we already said that being 0 means it's in the null cone and means that it cannot be scaled. So that's it's really the question about solving the null cone problem. So what do we know about this? Well, if you look at it, from a complexity theorist point of view, you say, okay, we look for an algorithm, but before an algorithm, we can look for a characterization, like is it in NP, is it in co-NP? So morally, you see that it's in NP in the sense that if the answer is 0, maybe I can give you a sequence of group elements that get it closer and closer to 0. So that's a witness that it goes to 0. But what do I do if I want to prove to you that it's, bounded from 0? Well, there is an answer, and that's in fact the answer that you always find in invariant theory algorithms books, and unfortunately it's too expensive. You can test that, there is some invariant which is non-zero on your input. The problem is that there are just exponentially many invariants, and typically, or doubly exponentially many, and each of them may be exponentially hard to compute. So that's not an effect. So you use Grobner basis and stuff like that. It's not efficient. But we are going to use a different way, and this analytic connection to this algebraic point, namely the really central Kemp-Ness theory, the duality theory of invariant theory. What does it say? This optimization problem gives a positive, bounded away from zero result if and only if something else is zero. If and only if there's some positive or non-zero vector in the orbit whose moment map, I'll say what it is, some function of it is zero, right? And let me first say this is a duality theorem, and it's a vast generalization of everybody's favorite linear programming duality. I will not explain it, but well, let me just say LP duality comes up if the group acting is an abelian group, is a torus. So this is a vast generalization of linear programming duality. The mu here is called the moment map, this function, and it's just a non-commutative analog of the gradient. So you should really see here something that's familiar for you. If you're looking for a minimum of a function, and you test the gradient to be zero. And another thing that takes an observation, at least in the cases we've done, and more generally can be defined so, minimizing mu is really a scaling problem. So making it zero is the same in the matrix scaling problem, is making it doubly stochastic, and in the operator scaling, making it doubly stochastic. So it's really dual to minimizing the L2 norm. And finally, I mean, the most important consequence here is explaining why do these greedy algorithms work. I mean, because of this duality, you know that when you find a zero gradient, you're not only at a local optimum, but you're at a global optimum, right? It certifies that your point is distant from zero. So you have convexity here, and this is what extends Euclidean convexity to convexity in arbitrary Riemannian manifolds that are the home of these matrix groups. So you can hope to employ it in this general context, this geodesic convexity, and that's exactly what we do. So yeah, I basically said both these things. So we are so I said that. So we go beyond alternate minimization. We don't need alternate minimization. We can think of maybe extending the usual tools of convex optimization, gradient descent, and so on, to this geodesic setting. And so that's exactly what we do. Of course, we did not invent geodesic convexity. It goes back to Gauss and Riemann. And we didn't even invent geodesic algorithms. There are books about it. What we do here is for these problems of interest, you'll see, well, certainly the null problem and more general problems that I'll discuss. We have, polynomial time algorithms, and more generally, quantitative complexity analysis. Sometimes, you improve doubly exponential to exponential. Anyway, you get a new quantitative convergence bounds. So let me say just at high level, what are these? So now, as I said, you think about action of arbitrary groups on vector spaces. I give you a vector, and I give you some epsilon. You want to approximate. Actually, there are two optimization problems here. To minimize the norm of an element in the orbit, or to minimize the norm of the gradient of any element in the orbit. I said that they are dual to each other, but when you talk about approximation, they are actually different problems. And for both, we have algorithms. What is the setup in convex optimization? You usually get Oracle access to the action. You have something describing basically the optimization functions you are after, and some of its derivatives. And what we get are, just analogs of the classical Euclidean results to this geodesic setting. In the first case, gradient descent, we get the algorithms like I showed you before that give you epsilon convergence in polynomial in 1/epsilon iterations. But if you allow me to use, and there's no reason not to use second order information, Hessian information of the action, then, like somebody else, you can get much faster convergence. Like you get in the Euclidean case, you can get polylog 1 over epsilon. Some people call it quadratic convergence, but I like to call it exponential convergence. And of course, both in this geodesic setting and in the classical setting, it's always a big question, what is this big O? And in both cases, the answer is the same. It depends on the smoothness of the function you optimize. And here the smoothness really comes from properties of the group action. And here comes some algebraic geometry and some representation theory. To understand these parameters, you need to understand the geometry of the weights of the irreducible representations of the action. But anyway, there are simple parameters to calculate in concrete cases and to see what the analysis gives in general. Okay, questions about this? I have one more round of about 5 minutes and then I'll be done. But before that, questions about this. That's the most general result, or almost the most general result we have. I'll generalize it even further in the next 5 minutes. But questions about this?
Avi, can you give an example, say in the case of finding in a lattice, finding the shortest point in a lattice, or something of this form where you can say what is the mu?
Well, I don't. It was not listed in my problems of applications, and I don't know how to approach it using these techniques.
A lattice, it's exactly a lattice. You have a group, and you're counting, and you're looking the minimizer of the norm.
No, I understand. I completely understand, but it's not a yeah.
I think my question is that in such a case where the group is abelian, is this mu function actually like a sort of discrete gradient, or is it something more?
It's a really great question, Leo. I just don't think it fits this framework, despite the fact that you are minimizing the norm of a vector under a group action given a basis for the lattice. And I think that I'm trying to have a short answer for why I think that, but maybe we should just discuss it afterwards.
I think the problem is that the set is discrete.
The set is discrete, yeah, absolutely.
Yeah, and in your setting, the set is
continuous.
Continuous, yes.
Yes, absolutely. Yeah. So, but still, given that you asked this question, I wonder if something, maybe indirect or clever can be said. But yeah, that's a very good answer. More questions? Okay, so this is general, and I want to make it just a bit more general. So I want to talk about non-uniform scaling and moment maps and moment polytopes. So just non-uniform scaling, you remember matrix scaling was trying to make a matrix doubly stochastic, namely make the row sums 1 and column sums 1. But actually, one can define non-uniform scaling of a matrix where you want some vector to be to represent all the row sums and another vector to represent all the column sums, and you can ask about convergence to this. And this turns out to be equivalent to a max flow problem, like the uniform was to a perfect matching problem. But in general, non-uniform scaling problems are very natural. They are basically what's called marginal problems. You want, like you have a bivariate distribution, the problem I just discussed, you have a bivariate distribution, and you want to scale it so that the marginals are specific. So I want to generalize everything to this non-uniform setting and tell you about these moment maps and moment polytopes in the last few minutes. So here's what we saw. We talked about group action, and we talked about the moment map, which is just non-commutative gradient. For those who know, I mean, in Euclidean spaces, this is the moment the gradient is just a vector with coordinates the same dimension as the Euclidean space you're acting on. In more general group actions, it will simply be the Lie algebra of the given group. So something that describes all directions you can go in. The uniform problem, which we discussed before, which was the null problem, was given a vector, you ask whether there's another vector in the orbit closure which has gradient 0, right? And the non-uniform one, instead of asking the gradient to be 0, you ask it to be something particular. I give you a vector and some other vector p in the whatever dimension we are at, and I ask you, is there a point in the orbit which has this particular gradient? Okay, so obviously it's a generalization of the previous one, and it turns out to be exactly the type of generalization like giving non-uniform marginals on a scaling problem. And yeah, what kind? We can handle this, but I want to first put it in really nice and amazing, in fact, for combinatorialists and geometers terms. Is that when you're faced with this non-uniform one, you can say, okay, let's ask the following question. I look at a particular orbit of the group action. What are the possible vectors that can occur as the gradients? So let's put them all in a set. Let's call delta of V all the gradients of elements in the orbit of V. Okay? Now I put a red star there just to say that you have to mod out by certain symmetries that you don't want. So I'm not going to get into this, but you take these vectors and throw out things that are redundant. But anyway, just think about this set of vectors. What is the structure of this set? What are, what can you say about all the gradients of points in the orbit of some vector given to you? And here's something absolutely amazing. It turns out it's an understanding that exists now for maybe 40 years, starting with work on Atiyah in Hamiltonian dynamics, Torah actions, and then Kirwan, Briand, and others. This set is a convex polytope. And you stare at it, nothing is obvious. Linearity is not obvious, convexity is not obvious, but it is a convex polytope, always. And I've never seen before I met this, any polytope that was not given to me either by the vertices, the convex hull of vertices, or by, the intersections of half planes. So it's really amazing. But it's sort of really happy, right? We have algorithms for testing this kind of things, and these are algorithms that actually test membership in polytopes, right? So, what polytopes? Well, we'll see. In moment polytopes, they are called moment polytopes. So I'll just give you, just picture of some of these polytopes. The main point is about this partition. I'm not going to run through all of them, but in the first part, the three top examples, you see, so let's read one of them. So the Schur-Horn set. I give you a symmetric matrix, and delta of A, and delta of A is going to be all diagonals of groups which are similar to A. Okay, so it's a set of vectors. This turns out to be a convex polytope. It's not so hard to prove directly, but just see it. It's not obvious at all, and the others are more complicated. In the bottom, you see examples of polytopes. They are defined by polytopes, like the Newton polytope of a polynomial, or the intersection matroid intersection polytope of two matroids. And you know they are polytopes, but it's not clear at all that there are any symmetries. You ask yourself, what are the groups? So all of these are moment polytopes. And because of this, we can apply algorithms to test membership in them. Okay, so let me just finish up. Maybe I should ask for questions here, so you see the slide, and then we'll wrap up.
Yes, I have a question.
Yeah.
Can you recall what Attia proved? He proved something for simplicial, I don't know, don't remember. So for simplicial things, like
Attia proved that for actions of tori on not just on Euclidean or on vector spaces, but even on manifolds, especially those that occur in Hamiltonian physics.
Yeah, but we need kind of simplicial group. Or
yes,
like
but in this case,
symplectic, not simplicial.
Yeah. Thank you.
Yeah, in this case, it turns out that everything is symplectic. I mean, for the tori action, and yeah, he proved that these are convex polytopes. This was the first result of its kind, and then it was generalized to non-commutative group actions.
Okay, thank you.
Yeah. Okay, so I'll just conclude. Some general themes we've seen. I mean, it's I said it several times. There's great interaction of algorithms and complexity theory with various mathematical areas. The problem we set out to solve is algebraic, but the algorithm is sort of analytic, continuous. And on the other hand, the analysis of this continuous algorithm is using algebraic techniques, presentation theory, and so on. So it's really sort of curious and beautiful. And it's really central message is that symmetry exists in lots of problems, often or sometimes we don't see it. I mean, if I tell you the perfect matching problem, it's not clear that there's any group action you should be interested in, but one group action is obvious, and using it you can find a new algorithm for it. So it's very powerful. Questions? Well, some of the algorithms are still exponential time, and yeah, there's lots of room for improvement. We don't know the extent of the power, especially for polyhedral combinatorics of this geodesic algorithm. So we have maybe a new algorithm for matrix intersection, but we already had one. So I want to see more applications, maybe for general matching. It would be great to have a matching in general graphs. I don't know whether this applies or not. Null-con problems are just everywhere. I mean, all the problems we've seen are almost are either null-con or moment problems. And maybe there's a general result that the null-con problem is in P. We just don't know that. There is a general result showing that in some form it is in NP and in co-NP. So this moral thing I said before is actually formal for a class of null-con problems, but yeah, it should indicate a polynomial time algorithm. It should indicate it in the same sense that the duality of linear programming, that it's in NP intersect co-NP, eventually led to the polynomial time algorithm for it. And yeah, all this was a detour, right? I mean, I told you, we want to solve this singularity problem for commutative variables. And this is important because it relates to the algebraic P versus NP question. So it would be great to have lower bounds for this. So we don't know. I should point out that there's a barrier result we proved recently with the Visu-Makam, is that all these algorithms solve the null-con problem, and you wonder whether the algebraic variety defined by the commutative singularity problem is a null-con. And what it really asks is, basically this: I give you an algebraic variety like this variety. What are the symmetries of this algebraic variety? I find it a very natural question. What we proved here is that for singularity, maybe that's a sign of its difficulty. And unlike the non-commutative case, it is not an null-con problem. So maybe you need more, and maybe these algorithms work in more general context. So I don't know. So let me stop with this and remind you of the book. Thank you.
Thank you very much, Avi, for the beautiful talk. There were many questions, but maybe there are more.
Yeah, so I'm open to all questions.
You still have to grab your lunch, though, I think.
Avi,
Yeah, I'll get there. Yeah, this is first food for thought and later food for stomach.
Well, Lior has a question.
Yeah, I wanted to ask about the commuting case. You're saying that it's not a null cone, so do you mean that the variety has no symmetries?
No, it has symmetries. It's in fact, it has the same symmetries that as the non-commutative case. It just has more. Okay, it has. Yeah.
So what does it mean? What does it mean? Not how?
There is no linear group. There is no linear group, so that this variety is a null group, is a null cone of this action. So we identify exactly the symmetries. So let me state a result of Frobenius that it is a generalization of, and this is what is behind the proof that it's not a null cone. Frobenius proved that characterize all the symmetries of the determinant. All right, what are the symmetries? You can apply any non-singular determinant one operation on the left or on the right to it, or you can take the transpose. And that's all. So out of all the GLN squared, out of the big group of acting linearly on all the variables, the n squared variables, only this subgroup is a group of symmetries of determinant. For commutative singularity, we need an analog for tuples of matrices, which we prove. And then we use it, once we understand exactly what is a group, we use it to show that it cannot be an null cone. And this is actually simple, but it has to do with the difference between commutative rank and non-commutative rank. But maybe I shouldn't get into this. But once the hard part is finding all the symmetries of this variety, and once you have it, then you see that it cannot be a null cone.
So is there a result saying that the null cone has only the symmetries of the group? Like the symmetry group of the null cone is the group?
Yes, but it's not a null, but yeah, so you identify all the symmetries, but the question is whether this is enough to drive any vector in the null cone to 0, and the answer is no, in this case.
Thank you.
Okay, yeah.
Any other question?
Oh, there is a question in the chat that Dima Zakharov asks. What is a good place to read about how invariant theory is used to prove a lower bound on capacity and other applications?
Yeah, so the first paper I mentioned, the paper with Gar Gurwitz and Oliveira, this is was published in Computational Mathematics a couple of years ago. All my papers are online in my website, so you can look at them there. This was the first result in this long series of papers, and it explains, I think, extremely well how invariant theory is used for this particular problem. Only yesterday we put online a revision of the final paper I mentioned, which does geodesic convexity on the archive. So it's updated and I think well written, and then you see how invariant theory much more generally allows the analysis of algorithms of this type. So this is, that's on the archive. So that's, and otherwise, any questions about references or questions in general, you can just send me mail and I'll answer it. So if you can find anything or you want your further questions you remember later, just send me an email.
Thank you very much. Anything else?
Avi, can I ask a question about your baby problem?
Yes.
Earlier, someone asked about the interpretation of the entries in the matrix that you get from applying Sinkhorn's algorithm.
Right.
And you said that these did not count the fraction of times an edge shows up in a perfect matching for some reason. What was the reason?
No, I found the counterexample. I constructed some, I believe, a bipartite graph with 3 vertices on each side with weights, right? It's a 3 by 3 matrix, right? So that, or maybe was it 4 by 4? I'm not sure. Small example where the numbers you get from this process are not the fraction of times an edge appears in the perfect matchings. So you in fact unweighted. So there's a simple graph for which what you get is not the fraction of times an edge participates in a matching. So it's just a simple counterexample. That's the reason.
Okay. All right.
That I don't have a, more intuitive. I really would love to know the meaning of these numbers. They must have a meaning. You realize that this answer is unique, right? What you converge to is unique. When there is a scaling, there is only one scaling. So these numbers.
Right. So I thought that since putting in the fraction of perfect matchings is a solution, and the solution is unique, that it must be right. But
yeah, what's wrong with this argument? I'm sure well, let me look at it again, and if my counterexample is wrong, and then it is true, then there is a deterministic approximation algorithm for.
But we know, for the permanent, yes.
Yeah. And it will be approximation because we just get approximations of this.
Right.
We can get them to be 1 + 1 over polynomial. So yeah, that's a very, thank you, Peter. I mean, I anyway was going to get back to this question and try to have a better understanding of what these numbers are, but maybe they are. Okay, I'll get back to you on that.
Great, shoot me an email. Thank you. Wonderful talk.
Thank you.
Yeah, thanks a lot, Avi. It was super interesting.
So thank you very much.
Okay, thanks for inviting me.
And anyone can listen to the talk any number of times on the website that Andre sent.
Yeah, and to many other talks, yeah.
Thanks a lot.
All right, bye-bye.
Okay, bye-bye.
Bye, everybody.